These are the notes for the last section of Chapter 18, which is 18-4, neutralization. We'll start out by talking about neutralization reactions, and these are reactions that we've talked about before, so they're not new, they're double replacement. So all neutralization reactions are a double replacement between an acid and a base. And if you remember the rules on double replacement, you draw a line on both of the compounds before the second capital letter on both of the compounds, swap the first partner. There's only ever two parts to each compound. You swap the first partner. So we see in this case base plus acid. And the base is sodium hydroxide, the acid is hydrochloric acid, and when we draw a line after the first caps and swap them, we end up with NaCl and HOH. This is a very important point in this chapter, that you need to know that when we add an acid and a base, the result is a salt and water. You need to be able to do these, so do some practice in your chapter. They have several of these. There's also some on the foldable practice. So make sure that you go through and try some of those. We're going to talk about equivalence. And equivalent is a very important unit that we talk about in neutralization. Helps us work with acids that have different numbers of hydrogens and bases that have different number of OHs. You remember that HCl is a monoprotic because it has one hydrogen. H2SO4 is diprotic. H3PO4 is triprotic. So this is a way that we could deal with those up front, easy, and we don't have to worry about the fact that some of them have 3 times as many hydrogen. So an equivalent, the definition, and we're going to talk about the equivalent of an acid first. An equivalent is how much of an acid provides 1 mole of H+. Now, for HCl, it only has 1 H, so obviously you have to have a whole mole. For H2SO4, we could think of it as double the amount of hydrogen because it has H2. We only need half a mole. For H3PO4, that has 3 hydrogens. We only need 1/3 of a mole to get 1 mole of hydrogens. So look at the subnumber below the H, and really it's if it's a 2, then you need a half a mole. If it's a 3, you need 1/3 of a mole in order to get an equivalent. Gram equivalent mass. Okay, now we've talked about molar mass. This is very related to that. In order to get the gram equivalent mass, you basically figure up the mass from the periodic table, the number underneath, which is the gram atomic mass, add that up for the compound. Remember the subnumbers, you multiply times the numbers on each of the elements. You get a total, which is the molar mass. We all know how to do that. Then you basically divide by the subnumber below the H for acid and the subnumber below the OH for bases. That's gram equivalent mass. Now, if you want to do dimensional analysis, we've got that worked out down on the bottom of the page. Notice that we got the molar mass, grams per mole, and then we multiply by moles per equivalent because we want moles to cancel and we want grams per equivalent. We end up 98.1 grams of H2SO4 that we got from the periodic table divided by 2 equivalents that we got from H2. Comes out the same way whether you do dimensional analysis or whether you memorize just molar mass divided by the number of equivalents below the H or below the OH. Our final answer on that one, once we've rounded, H2SO4 has 49.1 grams per equivalent. That's the unit for gram equivalent mass. Normality, also very important. When we work with normality, that is equivalents per liter. This is something that's not going to be on your possibly useful info sheet, so you need to know this definition of normality, equivalents per liter. So you know what an equivalent is. basically it's just instead of moles per liter, like molarity, it's equivalents per liter. You should be able to convert back and forth between molarity and normality. You'll see questions like that on the quiz and the test, on both of them. So we have an example, 2 moles of H2SO4, and we are multiplying the 2 moles of H2SO4 times 2 equivalents per mole. Notice that the mole in the first numerator and the mole in the second denominator cancel, and we end up with 2 times 2 equals 4 normal sulfuric acid. On the other problem, down at the bottom, we are converting from normality to molarity. 2 normal H2SO4, 2 normal sulfuric acid. When we convert it, we find out that that is 1 molar H2SO4. So this is why it's a little bit better to do dimensional analysis instead of memorizing, because on that one, from N to M, normality and molarity, you divide by the equivalence. On the other one, you multiply by the equivalence. So just be sure that if you just memorize what to do, that you go through drill and practice enough times on that, maybe some flashcards so that you don't switch them or mix them up. Dimensional analysis is always a good reliable. Look at that bottom area of that normality page on the notes and make sure you understand what's going on there. So acid-base titration. This is the lab that we're going to do. Actually on Friday we're going to do the titration of vinegar using sodium hydroxide. A titration is where we take 2 burettes, they're long, slender glass tubes that that are graduated, and they're very accurate, and they have a little spigot on the bottom. So we'll fill one with base and one with acid. In this case, the base will know the normality is 0.500 normal, and we use the formula that we're going to see on the next page of volume of acid times normality acid equals volume of base times normality of base. We're going to know the volume of the acid. That's what we read on the acid burette. We're going to know the volume of the base. That's what we read on the base burette. Once we've got them neutralized, and there's an indicator in the container at the bottom that will turn colors just when we have it neutralized, and that will solve for in this case, the normality of the acid. Page 667 in your text has the procedure and has the pictures of that apparatus, and we will be working on that in class, so you'll get to see it, and use it live. Okay, so that's decided to lock up. All right, we're going to move on with notes. I've got a copy of them here, so we'll just use this. After the acid-base titration, we move on to titration calculations. The titration calculation, we're going to use NaVA. NaVA equals NB VB. And B is base, A is acid. In this case, we're solving for the normality of the acid, so we're going to Anderson swap the volume of the acid down here. You know, if you want to do a little more conventional type of operation, you divide both sides by VA, you end up with the same thing. Na equals NB VB over VA. Like we said, you're going to know the volume of the base, the volume of the acid from the titration. You'll actually get them from the burettes. Or if it's a problem, it will tell you those volumes, and it will tell you the volume of the the normality of the base. We know these three. We multiply, divide, and we end up with the normality of the acid. So, again, we'll get some practice doing that. So next, we talk about salt hydrolysis. For salt hydrolysis, this actually can be a fairly complicated topic, but I remember in college it was one of the more complicated topics in chemistry, but we could actually simplify it. When you have an acid and a base, we know an acid and a base produce two products, salt, a salt, and water. Now when we say a salt, it's not always NaCl salt. It wasn't our first example, but depends on what you're mixing. You end up with a salt. Ionic compound is often called a salt because that's what they look like. They're crystalline solids. So when we mix an acid and a base, you generally expect to get a neutral solution, neutralization. But if it's not the same strength acid and base, you may not end up with a neutral solution. Here's the key to it. When you mix a strong acid and a strong base, they neutralize. But almost any other combination is going to end up with an acid or a base product. Strong acid, weak base, we end up with acidic. Strong base, weak acid, we're going to end up with a basic product. So it's a matter of knowing what your acids and bases are in strength. And if you have a chart, look up the chart. I'm going to give you actually 3 strong acids and 3 strong bases that I'm going to ask you to memorize. And that way when we get to this problem or question on the test, if it's not one of the strong acids, you'll consider it to be weak. Now we're doing this for the test. I'm not saying that there's just 3 strong acids. There are many strong acids. But for your use, if it's not one of those 3 acids, then consider it to be a weak acid. If it's not one of the 3 strong bases I give you, consider it to be a weak base. So remember, strong and strong, neutral. Strong and weak, whatever the strong item was, that's what you're going to end up with as the pH or the acid-base nature of the product. So the question will be asked several ways. It may ask you what's the pH of the product, greater than 7, less than 7, or 7. That's acid, base, or neutral. Or it may ask you, is it acid, base, or neutral? Same idea, same question, you just have a little bit different answer. So finally we'll look at buffers, and there's 4 things I want you to know about buffers. They're listed in the notes. First of all, what is a buffer? A buffer is a substance that maintains a constant pH in a solution. So if you add a buffer to a solution, there's buffers for pH of 1, 2, 3, 4, 7, 14, whatever you want to maintain the solution at, that's what the buffer does. Our body has several buffers that maintain a constant pH, and that's what is good for the cells, because the cells don't like big swings of acid, base, or salt, salinity, and too much fresh water, too much salinity. So we do in our body what we call homeostasis, which is maintaining a constant environment. Buffers are an important part of that. So what does a buffer do? It maintains a constant pH. We didn't say neutral pH. A constant pH. You could select a buffer and buy them for every pH, and it will keep that solution. If you add acid, let's say we had a buffer for pH of 6. You add acid, stays at 6. You add more acid, stays at 6. You add more acid, it stays at 6. You keep adding acid until we reach what we call the buffer capacity. And the buffer capacity is actually the number 3 item here. I want you to know what that is. It's kind of like the limit that a buffer can do. Once you get to that much acid being added, now it's going to drop the pH. It can't work anymore. Same thing happens on the base end. You can add base, add base, add base. There's a point where it won't keep the pH constant. That's the buffer capacity. Number 2 thing that I want you to know, what makes up a buffer? A weak acid or base and one of its salts. Finally, how does a buffer work? Well, you need to be able to explain to me either with a generic buffer, which we call like a HX type buffer where the X is the wild card, or I may ask you a specific one. But here's the thing. If you know the generic one, all you have to do is whatever the specific one is, that's the X is going to be what stands for instance, if it were acetic acid buffer, then you would plug in the acetate for the X. Acetate's one of your polyatomic ions. So be able to explain the general one, and you'll be able to substitute that X for something else. Or you could just do the whole thing with X and say, in this case, you wanted the acetic acid buffer, so X equals acetate, and then put the formula for it. So here's how it works. First thing, you need to be able to neutralize H+. How does that work? Well, you need to neutralize H+. The way we neutralize H+, is with the salt of the weak acid. How does that work? Well, when you drop this into solution, it splits, and you end up with X minus and whatever, or the H plus whatever X minus is. Well, the X minus is floating around, and when you dump acid in, that X locks onto the H, and remember, this is a weak acid. What does the weak acid do? Well, remember the example we used in class about the markers, that a weak acid doesn't separate into H and X. It stays together. Sometimes 99% of it will stay together. It's kind of like having a super glue bond here. You can't pull it apart. It doesn't come apart on its own. So what makes a weak acid is a strong bond with the hydrogen, and it won't let the hydrogen go. If the H+ doesn't go into solution, it doesn't have an effect like an acid, because that's the thing that makes it acid-like, is the H+. So weak acid locks that up and hides it, and now we've taken care of the H+. So H+ plus X minus yields HX, and the HX takes care of the H and hides it. What about neutralizing the OH? Well, for that, we're going to use the weak acid. Now remember, this HX doesn't want to come apart. The only thing that's going to make it come apart is if something pulls on it hard enough. And the thing that will pull on it hard enough is OH minus, because OH minus is very strong base. So OH will come up here and grab onto that H and rip it apart. So what does OH and H make? HOH, H2O, water. Water is neutral. And then the X minus floats around, and the X minus is ready to neutralize an H+ somewhere. And the X minus doesn't have a major effect on the acid-base nature. So that's how a buffer works. Remember, you should know what it is, what it's made of, what buffer capacity is, and how does it work. You need to be able to neutralize acid and base in an example, and that'll be on the free response part of your test. So that takes care of what we're covering for the last section. There's foldable for you to do some of these practice problems. There are also problems on the review. Go through, work that. Always you have problems in the book that are practice problems. Go work some of those. Work hard, study hard, and good luck.